Machine intelligence, we're all here, obviously, because it is a big deal. We believe it is a big deal. Possibly the biggest deal humanity has ever faced. Almost certainly bigger in terms of its societal impact than machine power was 250 years ago. And I would say, well, the positioning I would like to emphasize today is that there has never been a better reason to examine how we do compute, but also actually it is essential that we re-examine how we do compute for a couple of other reasons. And this is really the first time that we have had to reinvent compute from scratch since we invented it the first time about 75 years ago. There is a new wave of chip companies coming. Graphcore is one of them. And this new wave is inventing machines specifically for machine intelligence. There are chip companies selling billions of dollars worth of chips today into machine intelligence markets, but those chips were not specifically invented for this job. There's a new wave coming where they are specifically invented, and I think the market is big enough economically, but also the workload is different enough that that is a good idea, and that will eventually win. We call our offering into this market the IPU. All processors have to be called something PU, it appears. So I for intelligence, the intelligence processing unit. By the end of this 20 minutes, you should know roughly what that is. So here is a two-box picture of an intelligent machine. I apologize for its simplicity, but bear with me. There are two important components to any intelligent machine. What does an intelligent machine do? It has sensors that allow it to detect what's happening outside the box, and it has some sort of outputs that allow it to react in accordance to that. So it's a sequence-to-sequence translator. It takes a sequence of input data and it produces a sequence of output data, whatever it is. That's what you are. You're just sequence-to-sequence translators, with state, obviously. The state is your knowledge model. It's your accumulated wisdom. All that is a summary of all the data you've ever experienced. It's a massive probability distribution, a digest of all the data. And the other thing you have is you have the ability to compute on it, first of all, to produce that digest, and then to use that digest to decide what output data to produce. So that's the compute piece. So there's a compute piece and there's a data piece, and there are inputs and outputs, and that's it. That's what we are. That's what all machine intelligences will be. Okay. Everyone concentrates today on two types of computation, I think, for intelligence. People talk about training and inference. Training is, in fact, inference of the parameters, but we needn't get into that. They talk about training and inference. I get asked all the time, is your chip for training or for inference? Well, it's for intelligence. And actually, there are 4 pieces to intelligence, not 2. So training for sure. That means adjusting the parameters of a model that you have designed, a human has designed, usually, to improve the intelligence. There's also number 3 there, just beginning, which is how can we use intelligence to improve the design of the model? In other words, to evolve better structures, which we then optimize by learning. That has just begun. I think it was mentioned in a previous speaker. Number 2 has been mentioned earlier today, simulation. We don't really want interactions, many learning interactions between cars and bicycles. We'd rather that they were practiced offline. Actually, for safety, also because we can do it much faster. And a third one I haven't written down here, which is we can go and look for more data. In a simulation, we can produce bizarre scenarios. That was also mentioned by an earlier speaker. And those bizarre scenarios, they may be rare, but they're very useful for learning. And the final thing is that intelligence will turn a lot of things, a lot of products that weren't previously computers into computers. The car is the canonical example. There are about 7 times more cars sold every year than there are server computers. So if they all become computers, which inevitably they will over the next decade, whether they're completely autonomous or just partially autonomous, they will all become computers. Suppose they become a server each. That is a new market for computers that's 7 times larger than today's market for data center server computers. And it wasn't there the previous decade. So these are the 4 reasons why machine intelligent compute is really important and really valuable. Now the bad news. We are clueless. We're at the steam engines phase, by analogy to the machine power example. We're at the machine engine stage, steam engine stage of understanding what we need to build. And so all the stuff that came after the steam engines in the machine power analogy, like internal combustion and jet engines and nuclear power, electricity, we haven't invented that yet. That's all going to come later. It doesn't mean that we shouldn't develop these steam engines. Of course we must, and then we'll learn other things. But we are really at the beginning. We have a sense. I ask our customers, how much more compute do you need? They say anywhere from 1 million times as much to an infinite amount. It's never less than 1 million times as much. And I hope it's not an infinite amount, but it's somewhere in that window. And the bad news is that the capability rocket that computer science has ridden for the last 40-odd years of silicon geometric scaling and the improvements in performance, if you like, computation per second, that has brought, that is over. That is over. That rocket has run out of fuel. And that means not that silicon becomes useless, but that we must use it in completely different ways until something else comes along. And I think Iger is going to tell us what else is going to come along later. So wait for the next talk. So what can we rely on? What should we use today to guide what we build in this steam engines stage of evolution? Well, the historical lesson of the evolution of different computer architectures is that they primarily evolve to match the emergence of new data structures. In other words, a data structure tends to dictate the characteristics of any computing machine. So what is the fundamental data structure of intelligence? And the answer is, to go back to that 2-box picture, the answer is a graph. I don't mean an XY graph, I mean a mathematical graph of nodes or vertices connected by edges or links. The knowledge models that we're trying to learn are very high dimensional probability distributions. Because they're very high dimensional, they must be sparse, otherwise they would simply be too large. They would also be difficult to access data in. So what is the best data structure for a large, sparse graph? A large, sparse, multi-dimensional data structure? The answer is a graph. Each vertex represents a dimension. And the job of learning that knowledge model is the job of boiling down manifolds, possibly of lower dimension, in a very, very high dimensional space. Now, once you've decided that you want a graph for your data structure, actually that's quite a natural partitioning for the computation that you're going to do on that data structure. So the graph essentially represents the partitioning over a parallel computing resource of both of those boxes that I showed earlier, the knowledge model and the inference engine. Now, right down at the nodes of the graph, what's usually going on in a neural network, in deep learning, is that we are doing tensor arithmetic, low-dimensional tensors, typically 4 or 5 dimensions. And you hear a lot spoken today about tensors. There's TensorFlow, there's the tensor processing unit, there's tensor cores. Actually, the tensors, I don't think the tensors are very exciting. They're just like matrices with another dimension or two. We know how to do that stuff. We've been doing that for years. The really exciting stuff is not that. It's the graph. It's this billion-node sparse data structure that sits above the tensors. That is a real one, by the way. That's, for those of you familiar with ResNet, that is an image classifier trained on ImageNet. And that picture comes out of what I call the art output of our software development flow. It serves no practical purpose. It's just beautiful. Right, the other thing I said was that the capability rocket of Moore's law has come to an end. Now, the truth is, geometric scaling has not come to an end. We've got some way to go, maybe another factor of 10 to 100 in terms of geometry shrink, which is fantastic. But the bad news is that power has stopped us from exploiting that to get more performance since about 2005. And you can see this is the last decade of evolution of Intel Xeon processors, the big ones. And there are basically three lines here. I'm an engineer. I like this sort of graph as well. There are 3 lines here. The top 2 represent how quickly density is scaling. The number of transistors, logic transistors you can fit in a square inch, and the number of memory cells you can fit in a square inch. And that's going up roughly 2x per process node. A process node is now 2.5 to 3 years. So that's what Moore's law historically did. But the thing that didn't used to happen is the lower curve. And that is the rate at which we can increase the performance for a fixed power budget. That is only going up at root 2 per year. It used to go up at about 2 root 2, or even more than that sometimes, roughly 3x for each node. Now it only goes up at about root 2. And you see the impact of that because instead of faster processors, I mean, it's been a long time since Xeons and things like that in your laptop got any faster. All you're getting is more cores, but they're still the same speed. And that's because of this effect. What causes it is just the geometrical shrinkage of wire. It's got almost nothing to do with the transistors. It's just to do with the wire. Here's some pictures. These are roughly to scale, by the way, some pictures of layers of wire. Modern silicon process, we get about 15 layers of wire. I've just shown 3. And they are about that far apart, and they are taller than they are wide and such like. And generally, we alternate directions. And the capacitance between any one of those wires and all of its neighbors increases as you shrink the structure. And unfortunately, power is proportional to capacitance times the square of the voltage times the frequency. We used to drop the voltage quickly, especially with that square law effect, that we could allow the capacitance to go up, and actually we could drive the frequency up as well and still have the same power. And what's happened, what's known as the breakdown of Dennard scaling, is that we can no longer very much, we can a little, but not very much, reduce the voltage. So the bad news is, as we shrink, the power density goes up. And there are only 2 ways out of that problem. One is run everything slower. In that case, there's not really much point in shrinking. But your brain does run at about 100 hertz, so maybe there's something we can learn there. So run very slow. That won't help us with performance. And the other thing to do is not fill your chip with logic, not fill it with compute. If you fill it with compute, or if you attempt to fill it with compute, this is what's going to happen. This is the amount, so the square on the left is the biggest size of manufacturable die that any fab in the world can make. They're all limited by the optics of the machines that are used in these things. They can make a die of about 1¼ square inches. That's roughly how big our chip is. That's roughly how big the biggest GPUs are, the biggest CPUs, etc. And the fraction of logic that you can power at once in a die of that size is now about half the die, roughly the box in the middle. And as we go forward in process generation, that fraction will shrink. In other words, you'll be able to power less and less of the die. However, memory burns relatively little power. So you can fill the rest of the die with memory, and if you can find good utilization of that, that's the right thing to do. So processors, really powerful processors, will have less and less processing logic. They will become memories, mostly, with some processing scattered about. So the hard truth from silicon scaling is we'll probably get 3x in the rest of Moore's law, at least maybe over the next 3 process generations. Maybe it'll go further than that. We'll only get 3x. We want, what was it, 1,000,000x to infinity, I think I said. That isn't going to come from silicon scaling anymore. There was a time, but not anymore. So it has to come from new processor architecture, and it also has to come from bolting chips together. We have to get really good at using thousands of chips to solve these problems. And these are the design drivers of what I have called the intelligence processing unit, this new class of machine. All throughput processors are power limited, so they must be increasingly parallel. They must be mostly memory. The second point there is that it's not a law, but it's an observational rule of chip design that you get a pretty poor return on complexity of processors. If you want to double the performance of a processor, you have to spend roughly 4 times the number of transistors on it. So if you're interested in throughput, you're much better off putting a lot of very small processors in a box than a few large ones. Pollock's rule. So again, massive parallelism is implied. It is quite fortunate, therefore, that our fundamental data structure exposes massive parallelism. That graph exposes massive parallelism. So it's quite a good match. And the other thing is that writing parallel programs and getting them right is really difficult. And I don't mean writing a program that can run on the 4 ARM cores on your mobile phone. Then you could reasonably open 4 debugger windows on your terminal and watch the programs progress and send messages to each other, and that would be fine. What if you have to map to a machine with 1 million processors? You're not going to open 1 million debug windows on your screen. You're not even going to write 1 million little programs, obviously. You're going to have to write something else that generates 1 million programs. So this is a completely new world for the development of software. It's more than just new software, it's new software paradigms. The other thing is, how do you get 1 million processors or 1,000 processors to talk to each other and remain in order? So here's my advocation. There is one method which is safe and completely scalable, and it's called bulk synchronous parallel. And it basically has your machine alternating between a phase of compute in which everyone is computing just on data that is local to them. All of your little processors marked P there in orange are computing just on their local memory, marked M in blue. And they don't communicate with each other. So they're all asynchronous. And then when they've all finished doing work usefully on their local memory, then they all synchronize. They all agree what time of day it is, the whole machine. And then they go into this, what's called an exchange phase, where they all exchange information ready for the next compute phase. And in that exchange phase, there's no compute that goes on. They just move stuff from my memory to your memory. And then you go back round the loop. Now, this is not how computers operate today. But I think it is going to be how massively parallel computers operate today for 2 reasons. It's really simple, and it's safe. There's no other parallel processing idiom which is free of any sort of concurrency hazard. And if you're trying to debug a program with 1 million pieces, then it'll probably take forever unless you have that sort of safety guarantee. And it's very different because what I'm saying is you shouldn't overlap communications and computing. We spent the last 40 years trying to overlap communications and computing, trying to get everything to work at the same time. The roofline model that Kaz mentioned. The optimum on that model is the point at which they're both operating at the same time maximally. Well, in the new world, that's not what you want. That model is broken. And this is the reason. So, left column, this is what you design for. And normally you would design for you would be doing design in the top left corner. In other words, you're trying to overlap compute and exchange, communication. Now then you come to operate it and you discover that the ratio of compute and communication is not what you designed for. What happens? You underutilize something. In this case, you've underutilized compute. It still takes as long to run the program, but you underuse the power. Now, if power is your fundamental limit, then that's the wrong thing to do. Your objective, your efficiency definition should be to try and use all of the power available all of the time. If instead you had built a machine that serializes communications and compute, you would be on the bottom row. Your budget would still be the same, except you would assume you were doing all the compute first and then all the communication second, and then alternate that in whatever cycles you can manage. And if that ratio was incorrect, what happens? Instead of saving power, which you don't want to do, you save time. That's what we want. So the roofline model doesn't work anymore. All change. So here we are, 2018, 2 different plans. On the left is what everyone's currently doing. Big logic chip that I can't turn on all at once, connected to some DRAMs, which unfortunately can't be on the same chip, and are as close as I can get using very expensive technology called interposers and CoWoS. On the right, I think, is what we should be doing. And this is what IPUs advocate. and that is distribute a lot of very small tiles of memory and processor all over your chip and just bolt those chips together so that memory is always tight with processing and you operate in a BSP mode. And this is what we've built. It has 23 billion, 647,173,309 transistors on it exactly. And it was designed in Great Britain, and it is the most complex logic chip ever made. Its structure is exactly what I've just described to you. It has just over 1,200 little processors with memory, and they talk to each other over an exchange mechanism using a BSP cycle. It also has a bunch of external connections so that I can cluster these things into big groups. That one chip executes 7,000 programs in parallel. It's typically used in a cluster of 16, so I have about 115,000 programs running together to do one job. How do I do that? Very complicated. The important thing for you guys, no, the TV is about to turn off. The important thing for you guys is you don't need to worry about that because that's all in the tools. You program it in TensorFlow. Later on, you'll be able to program it in PyTorch and MixNet and everything else, but today, TensorFlow. Right, last slide, takeaways. I can't read that, it was powering off. Key takeaways. So the fundamental structure of intelligence is a graph of tensors, and frankly, the graph bit is the interesting bit, not the tensor bit, whatever the marketing tells you. By the way, tensor cores and tensor processing units, they don't actually process on tensors anyway. They process on matrices. Never mind. Throughput processors are all power limited, so they must become mostly memory. Either that or we have to reinvent some sort of new technology. The limits are very, very fundamental. They're to do with the transport of electrons in the band gap of silicon. So unless we change silicon or we change electrons, we're stuck with that. IPUs are processors designed for this paradigm, graph-centric, memory-dominated. And I advocate this BSP mechanism as the software abstraction for that sort of machine. Thank you. Great.